Okay, we are continuing our talk on regulating internal conditions of the body. So now we are going to focus in on thermoregulation, so the regulation of our body temperature. That's really important. So this involves the hypothalamus a lot and some other mechanisms. So the hypothalamus is located within the brain, kind of up in the central part of the brain. If you've already taken anatomy, this should be familiar. If you're in anatomy right now, we will cover this in a lot more detail later in the semester. But the hypothalamus is one of our many control centers within the brain. So it's going to regulate body temperature, by a negative feedback process. So it's basically the equivalent of the thermostat you have in your central heating and air conditioning system in this particular case. So normal body temperature is about 98.6 degrees Fahrenheit, which is around 37 degrees Celsius when taken with an oral thermometer, which is pretty common. It can be about 1 degree higher when measured rectally, and some other methods like the forehead detectors and in the ear can be a little bit lower or higher. So they're not quite as accurate, but generally they're pretty good, especially if somebody cannot have their temperature taken another way. But healthy adults can have resting body temperatures that are a little higher or a little lower than this, and that is their normal. Again, 37 Celsius, this is average. Not everybody fits perfectly into that average box. So it's about 5% of the population that has a body temperature that can be a little higher or a little lower. I'm actually one of those people. I tend to run around 96.5 Fahrenheit on average. So I tend to run a little bit on the lower side, but this is totally normal, and so I can get to a temperature of around 99 and feel like I am roasting. And so this is important because it can, in some cases, influence clinicians' treatment methods for certain things. It's just something to kind of be aware of. But other than that, this really doesn't have any clinical significance. It does not mean that anything's necessarily wrong, as long as that is a consistent normal body temperature for somebody. So outside of this, we are talking about temperatures that are significantly higher or lower than they are supposed to be. When we get up into the hundreds or down into the low 90s, 80s, even 70s, this is dangerous. This is significantly above or below homeostatic range, and specifically we're going to kind of focus in on body temperatures that are above that range. And this is a huge problem because this can cause enzymes to denature. Enzymes are proteins, so at high temperatures, proteins tend to denature and then they stop functioning. Temperatures above 109 Fahrenheit or 43 degrees Celsius or higher can actually result in death because it's basically just starting to cook different parts of the body, and proteins basically run our body. Not exclusively, obviously, but they are a huge part of running our body, so if we denature all of those, our body does not function any longer. So protein structure, we have different levels, and you can kind of compare this to telephone cords. So a single wire, that single initial wire within the telephone cord would be the primary structure. So this is very, very basic. So just our basic, this is all of the amino acids strung together. That is our primary structure. And then the coiled up cord of a telephone would be equivalent to the secondary structure. We can either have an alpha helix, so it's going to be the spiral shaped structure where these different amino acid groups are going to start interacting with each other. They're going to form some attractions. Or we can have a beta pleated sheet secondary structure. Same idea, different strings of proteins are going to have those groups on them start interacting together to form a larger structure. And then when a phone cord gets tangled or really coiled up in a abnormal way, this would be equivalent to a tertiary structure. So this is showing an alpha helix, and it kind of starts folding in on itself because these other groups on the proteins are still going to continue to start interacting with other nearby proteins, even within the same alpha helix in some cases. Not always. We can have a combination of alpha helix and beta pleated sheets together. There are a lot of structures we can make from these building blocks. And then if you get several telephone cords all tangled up together, then we have a quaternary structure. So an example of this is hemoglobin. So this is hemoglobin that carries oxygen in our bloodstream. It is a combination of 4 different tertiary structures all linked together. So different heat levels can start to break apart these different levels of structure. So as our body temperature increases, these start to break apart. All of these interactions between the different amino acids start to fall apart. So that's denaturation. So that process isn't necessarily strong enough to break all of the original peptide bonds in this primary structure. That stays intact, but it disrupts the quaternary, tertiary, and secondary structure levels. And that is going to prevent proteins from being able to do their job. And again, enzymes are proteins, and enzymes are essential for our body to function. So our hypothalamus receives input from some different areas of the body. We have peripheral thermoreceptors that are located in our skin. This isn't super important in stimulating the hypothalamus. Skin temperature can fluctuate quite a bit depending on what the surrounding air temperature is, and we don't want that to set off our internal control too much. But there are some times where we will activate either sweating or shivering mechanisms to kind of help maintain our core body temperature. And then we have central thermoreceptors that monitor the temperature of our blood. And these are located in the core of our body, so organs in the thoracic and abdominal cavities, and the hypothalamus. So these are a lot more important in signaling to the hypothalamus that something is very, very wrong, because our core body temperature should not fluctuate that much. A little bit, yes, but not significantly. All right, so we still have that negative feedback mechanism. If the blood starts getting warmer than our set point, that is going to activate the heat loss center in the hypothalamus. That activates a couple different mechanisms. Sweat glands get activated and we start sweating. As sweat evaporates, this helps cool our body. And then we are also going to cause dilation of the blood vessels in the skin, and that is going to allow a lot more heat to radiate from the surface of the skin. This will all lead to the body temperature decreasing, which decreases blood temperature, and the hypothalamus heat loss center shuts off because we've returned our temperature to pretty much normal. And then on the flip side, if our blood temperature starts beginning to cool, we are going to activate heat promoting centers in the hypothalamus. So in this case, we're still working on some blood vessels in the skin, but in this case, they constrict instead of dilate, and blood is actually diverted away from those capillaries in the skin temporarily, and it's kept in deeper tissues to minimize how much heat is getting lost from the skin. And then it's also going to activate skeletal muscles, and they are going to start contracting and shivering begin. So this is what shivering is designed to do, is to help us warm up, because as our muscles contract, they produce heat. This raises our blood temperature, and then it shuts off the hypothalamus. So again, dilation of the skin blood vessels. That way the warm blood can radiate heat off the surface of the skin. activates sweat glands. As it evaporates, it cools us down. This is why if you're not able to sweat, it can be very, very, very dangerous. There are some people who have conditions that can impact that. There are certain medications that can impact our ability to sweat. There are a lot of medications that can impact our ability to cool down. So if you take medications, it's definitely worth it to check and see if your medications fall under that class. I know SSRIs are one of them that can really mess with this entire process. So you have to be extra careful out in the heat. And then if we need to warm back up, we are going to constrict those blood vessels in the skin, keeping the blood further away from the skin so that heat is not being lost as much. And then those skeletal muscles start contracting, and that causes us to shiver, which produces a lot of heat to help us increase our body temperature. So sweating, again, evaporates. So we have a lot of water in our sweat. It's mostly water, and as water evaporates, it is going to cool because it is pulling heat with it as the water leaves. So water releases from the pores in our skin, and this has a lot to do with the chemistry of water. Water's a really cool substance. It has some very unique properties. So if the liquid water increases in temperature, average kinetic energy in it, energy from the movement of all the different water molecules, also increases. So basically this means that as temperature increases, the fastest moving molecules will move so quickly they break free of the other water molecules, which is evaporation. And they take that energy in the form of heat with them as they leave. So very, very cool process that our bodies have to help cool us down a little bit. So a nice breeze from a fan, or even if you're outside and it's coming from, natural mechanisms out there, this feels really, really nice because this also has to do with heat transfer. And as that air blows past your skin, it increases this evaporation. And so the heat's being lost even faster, which is why fans in the summertime are very, very, very popular to help keep that air moving. You've probably noticed, especially recently in this area, our humidity levels have been a bit higher than they normally are. They've come back down a little bit recently, thankfully. But as humidity increases, we sweat a lot more. This is because humidity has to do with how much water is contained in the air. And this impacts how much water can evaporate from our skin. So the rate that sweat in this case evaporates depends on how much water is already in the air. So on dry days, sweat evaporates really, really quickly because the air does not have a lot of water in it, and so it can pull that water from our body very, very easily. But on humid days, the air is already saturated, so sweat evaporates a lot more slowly because it doesn't have a place to go quite as easily as it leaves our body. So we sweat more because our body's still trying to cool us down, even though that evaporation isn't really happening. And so this is why high humidity conditions feel a lot hotter than they do in low humidity conditions. And if humidity goes up too much, our body's natural cooling mechanisms just cannot work very effectively. So this can be really, really dangerous. This can lead to heat cramps, heat exhaustion, heat stroke even. So humidity can be really, really dangerous. I remember being at a conference years ago, and it was in DC. The entire week I was there, except for the last day, it was like 85 to 90 degrees every day, which isn't the hottest. It's not terrible, but it was also like 85 to 90% humidity the entire time, and it was miserable. And I have never been so glad to be back in California with 115 degrees, but only like 20% humidity. And I know I have a cousin who used to work in the Gulf of Mexico. He was an underwater welder on oil rigs, and he loved coming back to California on his time off because it is so humid, and it is so much nicer when you have that low humidity and can actually sweat and have that evaporate and cool off. So one other case where our body temperature can increase a lot is fever. So this is a natural process that our immune system is involved in. This is an elevation of our core body temperature due to a temporary resetting of the thermostat in our hypothalamus. So the idea here is that our body can tolerate slightly higher temperatures better and longer than certain toxins or bacteria or viruses can. So a common cause of fever are the release of something called an endogenous pyrogen. This can come from phagocytic cells, which can be triggered by viral or bacterial infections, and in some cases bacterial toxins. And so this is a mild increase in temperature, in that core body temperature, because we've temporarily reset the thermostat in our hypothalamus, because it can help increase our immune system response and help inhibit bacterial growth. Most bacteria and even viruses have a very, very narrow range that they grow optimally at. And so if we increase that too much or decrease it, then that is going to slow down the growth of those bacteria or viruses, which give our immune system even more of a boost because it has a chance to kind of get ahead of that growth. So fever caused by bacterial infection, a lot of this also applies to viral infections. So macrophages and other phagocytic cells in our immune system will engulf those bacteria, and they can be stimulated to release a lot of cytokines. There are a lot of different types of cytokines. We're going to focus on pyrogens. So pyro means fire, gen is produce. So these are heat-producing substances. One of them is interleukin-1 or IL-1. This circulates into the hypothalamus, which increases prostaglandin secretion. So those neurons in the hypothalamus start secreting something called prostaglandins. We again have several of these that have different functions throughout the body. They are also involved in menstrual cramps, believe it or not. So they have a lot of different functions. But these specific prostaglandins being produced in the hypothalamus actually reset that thermostat to a slightly higher temperature. This can be, for example, about 39 degrees Celsius or 103 degrees Fahrenheit. That is definitely a fever. So somebody's running a fever, running a temperature. There's some different ways that that's said in common language. So this is again, temporary reset of that thermostat. So they are localized chemical mediators, in this case acting directly on the hypothalamus. But because the hypothalamus controls our core body temperature, we feel it throughout our entire body. So these heat-promoting mechanisms now activate. All of those heat-promoting mechanisms, the shivering, the vasoconstriction of cutaneous blood vessels, those are all going to activate because we have temporarily reset our core body temperature to a higher level. So now the body is thinking, well, we're too cold. We have to bring up the body temperature. So that is going to get activated. This also increases our metabolism. So even though our core body temperature is higher than it's normally supposed to be, we are still going to activate these mechanisms because of that temporary reset. So the skin stays cold, shivering occurs. So this is called a chill in common language. So this is a pretty definite sign that core body temperature is rising. And after several hours of this, the core temperature can reach that temporary new thermostat setting. The chills will disappear, but now the body is going to continue to regulate the temperature at that new setting until that influence of the pyrogens is removed. So once the bacteria are gone, and then the phagocytic cells are done with their job, and they are not releasing those pyrogens anymore, then the thermostat resets back to its normal baseline level. Again, the average is 98.6 Fahrenheit or 37 degrees Celsius. So normal body temperature is still high at that point once that's reset. And it's kind of like if you were to set your central AC thermostat, you know, maybe it warmed up too much in your house, and so you turn it down lower. And so now it needs to cool things off. So now we are going to activate those heat-losing mechanisms, so vasodilation of the skin capillaries and a lot more sweating. So this is going to trigger the skin to feel warm, person starts sweating. So this phase of the fever indicates the core body temperature is falling. So this is commonly referred to as a broken fever. So the fever's broken finally. There are medications out there that can help kind of moderate this process. So antipyretics, so aspirin and ibuprofen, even Tylenol, acetaminophen can fall into this category. So they reduce or relieve fever by inhibiting the synthesis of certain prostaglandins in the hypothalamus. And so that helps inhibit the effect of pyrogens to reset that hypothalamic thermostat. So a lot of these medications fall into the non-steroidal anti-inflammatory drugs class, or NSAIDs. So these are drugs that reduce inflammation, which is pain, fever, and swelling. So this is aspirin, ibuprofen, naproxen. So the brand names there are Advil, Motrin, and Aleve. So drug names and brand names, they're going to do the same thing, even if you buy the generic store version. So aspirin, though, does not lower the temperature in a person that does not already have a fever because of in the absence of those endogenous pyrogens, prostaglandins are not present. But Advil and, or not Advil, Motrin and Aleve can still kind of work to a certain extent. But we will go over this a bit more when we cover the immune system later in the semester. So again, that fever and chills is due to the pyrogens being produced by our immune cells, which start producing prostaglandins locally within the hypothalamus, which temporarily increases our normal core temperature to try to slow down bacterial or viral growth and let our immune system cells kind of catch up and overtake those. And then once that infection is cleared up, then the pyrogens stop being produced, which stops signaling the production of prostaglandins, and then the core temperature gets reset to its normal baseline. And that wraps up the second video. Our last one, we will talk about scientific method and different types of studies.